in today's questions, we were supposed to answer what would be the impedance and phase angle of a series RLC circuit at resonant frequency. Well, at resonant frequency, actually, I gave here extra information because, in principle, I could even hide the information that impedance of the inductor and the impedance of the capacitor are 1 kilo ohms, because at resonant frequency, a resonance happens when the two impedances are equal. And if these two impedances are equal, when we combine them, they will add up to a zero impedance. Impedance of inductor and capacitor connected in series, if the impedances are equal, it adds up to zero. And the reason for it is that the phases are opposite. So remember that when we combine impedances, we don't just add them like resistances. We have separate rules for these. Now, we can add complex impedances the way we add resistances. And if the elements are connected in series, complex impedance of the combination of inductor and capacitor would be I omega t plus 1 over I omega c. Well, if I bring this, I mean, because, so in other words, if I factor out I will have omega L, which is impedance of the inductor, minus 1 over omega C, which is impedance of the capacitor, and if these two impedances are equal, they add up to 0. So if the three elements are connected in series, despite each of them has impedance of 1 kilo ohm, the combination also has impedance of 1 kilo ohm. Now the phase angle, and again, complex impedance is really helpful because we can find out phase angle by considering real part of the complex impedance and imaginary part of complex impedance. And well, we have to take arctangent of the ratio of the two parts. And if imaginary part is 0 and real part is not 0, then quotient of imaginary part of complex impedance over real part of complex impedance is going to be 0. Therefore, phase angle is going to be 0. All right. Yesterday we spoke about a circuit which we refer to as high-pass filter, and if you recall, high-pass filter has such a property that at high frequency of current, gain of that circuit is close to 1, and at low frequencies it's close to 0. So if we have a combination of a number of frequencies in the signal, the low frequencies will be eliminated from the signal and high frequencies will pass through that filter. Now, low-pass filter, the name already indicates that it works the other way. Low-pass filter will now transmit signal with low frequency and block signal with high frequency. And an example of a low-pass filter is a combination of a resistor and capacitor. It's a similar, I mean, practically the same elements as in a high-pass filter, except that they are arranged differently. What's the difference? Well, in high-pass filter, resistor is here and capacitor is there. Right. All right. Now, so imagine now that we have a certain source of signal connected to the input of the low-pass filter and something else. It will be most likely a stage of an amplifier connected to the output. And again, for the filter to work properly, impedance of this fragment must be high. So input impedance to that amplifier, for example, has to be high. Now let's see now how let's do the same calculations. Let's relate output voltage with input voltage and both. Root mean square value or peak value, I forgot what we related yesterday and what I have on this slide, and the phase angle. All right, so let's start with the complex output voltage. So complex output voltage is voltage is across the capacitor. So well, because of that, complex voltage across the capacitor is equal to impedance of the capacitor, complex impedance of the capacitor, multiplied by complex current flowing through the capacitor. Now, this complex current flowing through the capacitor, I again recognize that the resistor and capacitor are connected in series. Now, it's approximately in series. How approximate? It is as approximate as no current flows through the input of this amplifier. So if input to this amplifier is high, has high impedance, then current practically flows only through a resistor and capacitor. So the two currents are equal, and if the two currents are equal, it means that these two elements are connected in series. So I can find easily equivalent complex impedance of this system, because it will be complex impedance of the resistor plus complex impedance of the capacitor. And when I have complex impedance of the system, I can relate now current flowing in the system, or complex current flowing in the system, with the complex voltage across the input. All right, so I'll do that. Complex voltage across the input, or across that circuit, is the complex input voltage, and elements are connected in series, so I add the two complex impedances. And the rest thing is just algebra. I will simplify it a little bit and write down that output voltage, complex output voltage, is complex input voltage multiplied by this number. Now, what will be the name of this number? Proportionality coefficient between input and output voltage is referred to as gain. Yeah, so here I have complex gain. All right, let's now relate root mean square or peak values of those. Peak value of the output signal to peak value of the input signal. So what do I have to do? Well, if I have complex voltage, in order to get peak value, I just take absolute value of that number. So I have to take absolute, if I take absolute value of the output voltage, it means that I have to take absolute value of this number as well. Absolute value of a product is equal to product of absolute values. And absolute value of this denominator is 1 plus omega RC squared. I mean, in principle, 1 is also squared. And tangent of the phase shift between the two signals, well, it will be imaginary part of complex gain over real part of complex gain. I mean, now we would have actually to kind of rationalize it in order to determine what is the imaginary part. This I has to be in the numerator. All right. So let's now analyze what happens at what frequencies. So let's say that input, then we have input voltage of various frequencies of the same peak value, let's say 1 volt. And see what will be the output at those various frequencies. So if frequency is small, well, if frequency is small, which means that angular frequency in the denominator is also small. So this number is close to 0, and I will have, and gain is going to be 1. So at low frequency, why don't we start drawing it? So at low frequencies, gain is close to 1. At 0 frequency, it will be exactly 1. Now, as frequency goes up, this number becomes higher and higher and higher. So gain gets smaller and smaller and smaller. And at very high frequency, this number is huge. So 1 over huge number is 0. Gain is going to be small. So now the plot of the gain of such a circuit is going to be, well, 1 or close to 1 for low frequencies and 0 at high frequencies. Now, when we transmit a signal, because I mean, let's think that we speak to a microphone. When we, well, I speak to a microphone. And when I speak to a microphone, actually, my voice produces a lot of frequencies in the signal, and now, in order to recreate that signal properly on YouTube, I mean, if I use a filter, it has to be that all frequencies won't be shifted with phase, so that it can be recombined properly. Well, it happens that indeed this is how it works. Because if I think about low frequencies, when the signal is transmitted, I can recognize the tangent of the phase shift is close to 0. So indeed, there are no phase shifts between various components of the signal. At high frequency, by the way, I mean, notice that there is a phase shift, because at high frequencies, this expression goes to -infinity, and tangent of -infinity is -π/2. All right, so we will have phase shift between the signals over there, but we don't care it because it is not transmitted anyway. So for the operation of low pass filter, we don't care about it. All right, now why don't we take a look how it behaves, how the real circuit behaves. So I have assembled here the circuit. You can recognize this is low the ground or reference potential from the power supply. So this is 0 on the diagram, and I connected capacitor to it, and the other terminal of the capacitor is connected to that rheostat. Rheostat is a resistor for which I can change the resistance, and this is connected to the high potential. And now, with this one, I'm going to take the signal. So this is that point out. Where should I connect it? I connected already one side to the reference. Where should I connect this in order to get the signal, the output signal from the low pass filter? Where? Here? No. No, that way I would connect to the reference. However, Owen is right. I have to connect it to the capacitor. It has to be between the capacitor and the resistor. So I'll connect it here. And this way I have I assembled already the circuit. Okay. So now I need to put laptop here. All right. Now let's see that we interpret properly what is what. Yes, so the red plot is the, well, it says output voltage, but it's really output from the power supply. So in the circuit, for the circuit, the red one is the input to the filter, and voltage from channel B is the output voltage. Well, so let's right now see, how about if we actually go to start with low frequencies. All right. I wonder if 1 hertz will work better. All right. So actually, this low-pass filter is very low-pass filter. So let's start with frequency of 3 hertz. We have now frequency of 3 hertz. Both scales, output voltage and input voltage, are 1 volt per division. So what is the value of input voltage, peak value of input voltage? Why don't you shout? 4 volts. Input, peak value of input is 4 volts. What's peak value of the output? Also 4 volts. Well, estimate the gain of the circuit now. How much? 1, right? The gain is 1. Look actually that the signal is exactly, the output signal is exactly the same as input signal. Right? Well, I mean, there's just tiny phase shift, but they almost overlap. And now I'm going to increase the frequency. All right, now I have 10 hertz. Well, I still can see that practically gain is 1. All right, let's now make steps of 10 and how about 50? 50 hertz. What happened to the gain now? It decreased. What is the gain now? 3/4. The gain now is 3/4. So if I make a plot of this curve, we already got through that almost flat part, and now we are on the slope over here. So let's find out, for example, at what frequency, because this frequency is the one which characterizes a filter. It's approximately these frequencies are transmitted. We say that whenever gain is 1/2, so these frequencies are almost transmitted, these are almost blocked. All right, so let me increase the frequency more. All right, so now at 90 hertz, we are at this point. Yes, so we would say that this filter cuts off frequency at 90 hertz. So actually, if this filter was in that microphone, I would probably speak like that. Yeah, through the speaker. Yeah, my high frequencies would be cut off. Only low frequencies would transmit. Yeah, because I speak with frequencies about between probably 50 and 500. I mean, few hundred. I mean, the pitch of a person is few hundred hertz. All right, now let's go even to further frequencies, higher frequencies. So how about 200? At 200, we see that gain is 1/4. And how about further? You see that the higher the frequency, the smaller is the gain, really resembling this plot. Why don't we actually take a look at the what are the consequences? So let's say that I will go to lower frequency, something like 10 Hertz, and have a different shape of a function. All right, so now instead of sine wave, I'll put square wave. Let me stretch it a little bit. So actually you see that because we are missing those frequency, the output does not resemble the input. In order to really to create a square wave, we would have to combine a lot of frequencies. If I miss these frequencies, this is what happens. And let me see if I can actually observe some other effects. I mean, right now we are just seeing charging and discharging capacitor. The shape. I mean, we have already seen this. This type of a shape. All right. I still want to talk about the same circuit. However, I want now to call it differently, because I mean we are smart creatures, and depending on this, what is our need, we can take advantage of all possibilities. Over here, for example, we have that. I mean, in the low-pass filter, we really take advantage of this fragment of that gain plot. Now this is not wasted. We figured out how to take advantage of this part as well. Now, over here in this range, what happens is that impedance of the capacitor, this impedance, is much smaller than the impedance of the resistor. I mean, it's obvious, because I mean, really, you can even look at this circuit like a kind of a voltage divider. You remember how when we arranged two resistors, then the voltage across the two resistors was across one resistor was a fraction of the voltage across the two resistors, with the ratio determined by resistances. Well, here we can have the same kind of the same thing. Voltage across the two one element is a certain fraction of the voltage across the two elements together, determined by the ratio of their impedances. So, well, if a certain current over here flows, and think for a moment in terms of complex current. If we have certain complex current, and the relation between impedances is that impedance of the capacitor is much smaller than impedance of the resistor, then complex voltage across the capacitor, how complex voltage across the capacitor will be related to complex voltage across the resistor. Compare them. Well, their absolute values will be related also by the same relationship. Therefore, peak value of the voltage across the capacitor is going to be much smaller than peak value of the voltage across the resistor. I can even think about it that the ratio is practically zero. So even if I can measure over here a voltage, compared to the voltage across the resistor, voltage across the capacitor is zero. Well, so compare then voltage across the resistor with the voltage across the entire circuit. They will be approximately equal, right? So I can make an assumption that if make conclusion actually that if if impedance of the capacitor is much smaller than impedance of the resistor, then the input voltage is the same as voltage across the resistor, right? Well, how about then if I will relate the output voltage to the input voltage, and output voltage is the voltage across the capacitor, and voltage across at any instant, voltage across the capacitor is equal to the charge on the capacitor divided by the capacitance of the capacitor. Now, charge on the capacitor is equal to the integral of the current flowing through the capacitor, right? I mean, we saw the other way, that the rate of change of charging capacitor was equal to the current. So if I reverse this relationship, I will get that charge is equal to integral of the current. Now, I can write that this current is equal to the, well, this current is current really flowing through the capacitor, but it's the same current as flowing through the resistor, and current in the resistor depends on the voltage across the resistor, which happens to be approximately equal to voltage across the system. So I can put it that current through the resistor is approximately equal to input voltage divided by resistance. Well, I get relationship now between output voltage and input voltage. What is the relationship? Output voltage is proportional to the integral of input voltage. And because of that, we call it an integrating circuit. So now I can create certain signal and which is a certain function, and the output is going to be the integral of this input. Well, why don't we actually check it on that circuit which we have here? So at what frequencies should I do that? At what frequencies impedance of the capacitor is much smaller than impedance of the resistor? Which one? Yeah, when this condition is true. No, hi. I was just showing that we don't waste this part. We use this part as a filter, but we don't waste this part either. All right, so we have to use high frequencies. All right, I'll change now to the laptop, and change the frequency to high one. How about even higher? All right. Now I'll let you to think for a while. You can even talk to each other. Does it work? And what works? Did we get what I just said? How about actually I will ask somebody maybe to anybody would like to give a comment? Jerry, would you? No? Oscar, how about you? Do you feel comfortable? Do you see the point? Well, why don't you talk for a while? What was the point, and do we see it? Should I maybe bring up the slide for a moment? All right, just for a moment. Here was our conclusion. And can somebody phrase the conclusion? Jerry, would you be able to do that? Yeah, why don't you say it, yeah?
the output voltage is equal to the integral of the input voltage.
Yeah, it's proportional, precisely.
Yeah.
Correct. The output voltage is proportional to the integral of input voltage. Repeat it to your neighbor. Right. Now, consult with the neighbor to make sure that you both comprehend what did you just repeated. All right. So now how about if we take a look at the plots? Now, which one is the output? Which one is the input? I mean, the numbers, the descriptions actually here are kind of confusing, yeah, because this output over here, the red one is the input into the circuit. It's output from the power supply. Yeah, but red is the input, and green is the output. All right, so how about if we think about, let's say, this interval? If what? Adam, why don't you give your comments to the public?
Well, like when you...
Yes.
Oh, like when you do an integral, you're measuring the rectangle area of it, and since the output...
Right, and now which one we integrate, the red or the green?
We're integrating the red.
We integrate the red, okay. Now, if I consider just, let's say, this interval. In this interval, what is the shape of the integrated function? What function we integrate? Let's say f equals how much? Not 1. 4, correct. And it's a constant function. Do you see that?
Yeah.
It's a constant function. Well, what's the integral of a constant function? A linear function, correct. And do we have a linear function?
Yeah.
Approximately. I mean, you can see that it's approximate, right?
Linear.
Because I mean, I still see that it is that it's both a little bit, right? All right. Now, how about if we consider this interval? What is the value of the function? Yes, Adam.
-4.
-4. Correct. So it's negative. What will be integral of -4?
Linear slope, negative linear slope.
Linear function with negative slope. Correct. And then precisely that slope will be -4 if we integrate it. However, in front of the integral we have this 1 over RC. All right. How about if I show you different functions? Now here are the choices. Okay, I can put triangle function. Triangle function looks like that. I mean, this will be interesting. I want you now to make prediction. Yeah, this is the type of a function we are going to have now, I think. Yeah, so let's consider this interval. Oh, I should actually, it would be better if I could make it in red. Yeah, so this is the input. What's integral of a linear function? A quadratic function, correct. So how the plot is going to look like?
Be a curve.
A fragment of a parabola, right? I think something like that. And then, what will happen then?
So it gets negative.
So what will happen? I mean, I'm not sure if it will be exactly that way, but what will happen now?
Curve should go down.
Reversed parabola. Yes, so we'll have parabola upside down and up, up and down. Okay, and indeed this is what we have. Right? We have a fragment of parabola here, fragment of parabola here. It's hard to say if it is parabola or sine function. So how about then if I take ramp up functions? Yeah, so this will be easier. Oh, yeah, I like that. Does it work? Yeah, because now whenever we have a linear function, yeah, it's a fragment of parabola. Now we recognize over here that since well, the value of the function drops to negative, so now we have the function which is falling down, right? Now this was up. I see a ramp down wave. What will happen if I switch to this one? The parabola switch will flip. Oh, wow. Isn't it great? I wonder actually if positive square wave will work. No, it doesn't. And this is what I actually thought, that it won't. Can you figure out why? I mean, let's take a look at the circuit. Yeah, why it doesn't work when we have only positive input? Anybody has Andrew will have an explanation.
My thinking is the capacitor never discharges then, it only charges, so...
Very good.
Yeah, after
the
time
capacitor is being only charged. So the output potential goes up, up, up. I mean, really it could work kind of if the input to the amplifier, that load on the right hand side, the yellow load on this yellow load has relatively low impedance, so that the capacitor has a time to discharge. All right. Now, have you already had RLC circuit in the lab or not? When you have it, I mean, if you have spare time, play with it. Yeah, you can build various circuits and make various relations, because I mean, as I remember over there, it's you are just looking for a resonant frequency. So and most likely, I mean, at least I know that engineering students usually finish their lab earlier. So if you finish this lab earlier, play with the circuit. All right. I wanted really to tell you how a radio works. So, and actually, these elements, the other electrical elements are also listed in the book. So the homework, for example, will involve a diode. I want now to talk today and tomorrow about other electrical elements which we find in a TV set or radio set and electronic equipment. Diode is a very important electronic element. This is a symbol for a diode, and diode is an electrical element which also has two sides, and in a way it behaves like a resistor with an isotropic resistance. Depending on this, how we polarize the diode has either low resistance or high resistance. So if the diode is, we say, forward biased, and forward bias means that, I mean, consistently with the symbol, that we have higher potential on this side than on that side. If potential here is higher than potential there, the diode has low resistance. If potential on the right-hand side is higher than potential on the left-hand side, the diode has high resistance. You can think about it that it conducts this way and insulates the other way. Contemporary diodes are made from semiconductors which well, have two types of conductivity. We have to make a junction. We bring together, let's say, differently doped pieces of silicon, or a lot of other semiconductors. Important thing is that in one of those semiconductors we have positively charged particles which carry current, and in the other one we have negatively charged particles which carry current. These positively charged carriers are referred to as holes, H-O-L-Es, and negatively charged are obviously electrons. Holes are really missing electrons. Now, if we arrange a circuit in such a way that higher potential is on P side, so electric field now is to the right, well, it means that the holes, the positively charged particles, will be transmitted to the right, pushed to the right. Electrons will be pushed to the left, and they will be resupplied by the wire on one side and the other side. So if I consider this junction, I will have current flowing through the junction. And if current flows through the junction, it is a cross-sectional surface of that loop. So this is going to be the current in the loop. So in forward bias, we have such a situation. And in forward bias, if I draw the plot of the current versus applied voltage, actually it's not a linear function like in a resistor, but it's an exponential function, and pretty steep exponential function actually. It grows very fast. So at 1 volt, if I connect 1 volt to a diode, there will be a large current flowing through the diode. Now, if I reverse orientation, then the positively charged particles will be now moved away from the junction, and negatively charged particles will be moved away from the junction. So practically there will be no current flowing through the junction. Now, it happens actually that in p-type we have few wandering electrons, and in n-type we have few wandering holes. They are referred as minority charge carriers in the corresponding materials. So even if a diode is reverse biased, there is a tiny current flowing in that reverse direction. I can recognize over here that it is not exactly zero. There is a tiny current flowing in the reverse diode. Now, depending on the application of the diode, we want this current actually to have as small as possible. But we even have a diode which actually which is referred as avalanche diode or Zener diode, in which we take advantage that eventually, if the field is sufficiently strong, those minority carriers can acquire such speed in their materials that they will knock out more carriers. They will generate carriers. They will produce an avalanche of carriers. So electrons will bump into atoms and knock out more electrons. So eventually, minority carriers actually become very numerous, and we have kind of a discharge in the diode. And for a particular diode, it happens at a precise potential difference. Therefore, Zener diodes are used to stabilize voltages. This avalanche happens at a particular voltage. And I think I don't have enough time to go through the application of a diode in a rectifier. Therefore, we will end the lecture here, and I will come back to this tomorrow.